This video will discuss the WACV 2026 paper titled SCATR, Mitigating New Instance Suppression in LiDAR-based Tracking by Attention via Second Chance Assignment and Track Query Dropout, written by Cheong, Letian Wang, Sandro Papais, and Stephen Waslander. Tracking by Attention, or TBA, uses transformers to perform tracking in an end-to-end manner. Learned track queries represent individual tracks in the scene and are used to predict the locations of the specific objects that they're associated with. Track queries are propagated to predict the location of the same object over multiple iterations. Proposal queries are used to detect objects that have not been previously tracked and are added to the track query set to be propagated into future time steps. Below is a diagram of the SCATR architecture following the standard TBA paradigm. Proposal queries perform an initial detection with a detection decoder. The top n proposal queries are concatenated with the track queries from the previous time step. The track decoder then performs detection and tracking using all of the queries. Track queries detect the location of their associated objects, while the proposal queries detect the location of any untracked objects. Although TBA methods have been able to outperform tracking by detection in the 2D and 3D vision domains, 3D LiDAR TBA methods have not seen the same advancements, exhibiting high false negative error rates. These false negative error rates are caused by low confidences from the proposal queries compared to the track queries, the rarity of newborn track cases leading to proposal queries being undersupervised during training, and the suppression of duplicate proposal queries regardless of their quality. In the figure on the right, we see that the proposal queries are assigned to a negative prediction during training if the object that they're detecting has already been detected by a track query. In order to reduce the false negative errors in LiDAR TBA, SCATR proposes methods of better detecting newborn track instances. One approach to addressing this is to improve the proposal query confidence. Previous work found that track queries are more confident than the proposal queries in LiDAR TBA. To address this gap in confidence scores, we focused on distinguishing between which proposal queries are duplicates of track queries and which queries are unique. This leads us to the first innovation of SCATR, which we call track query dropout. In the left figure, we consider a case where there's both a proposal query and a track query corresponding to object B. The model is expected to output a high confidence detection for track query B while suppressing proposal query B, since object B is not a newborn track instance. However, on the right, we consider object B instead to be a newborn track, such that there is no track query already corresponding to object B. Proposal query B in this case is still identical to the left case, so the only difference is the absence of track query B. The model is expected to output a high confidence prediction for the same query since it's not a duplicate of any track. This expected behavior of the transformer is fairly complex and dependent on what track queries are actually present. This led to the creation of a simple augmentation designed to better train the decoder to handle this reasoning. Track query dropout involves creating multiple groups of queries during training by removing track queries from the query set. These groups can be passed in parallel to the transformer decoder, similar to batching multiple samples. By using these multiple groups, the model is exposed to both query scenarios in a single forward pass and does not rely on penalizing proposal queries for predicting objects. Track query dropout is only used during training. During inference, no queries are dropped and only the original query set is used. Returning to our original motivation, we want to reduce the false negatives by detecting newborn tracks better. One way of doing this is to improve the proposal query confidence, which led us to track query dropout. However, in addition to this, we also explored directly strengthening the detection of newborn track queries. What if we also allowed track queries to detect newborn tracks? We already know that track queries are more confident than the proposal queries, so why don't we leverage this? Here we have the standard TBA ground truth assignment process during training. Given a set of track queries and proposal queries, the ground truth objects first undergo direct assignment, where the track queries that have already been assigned a track ID get assigned to the same ground truth track. However, not all track queries already have a ground truth ID as indicated by the grayed out track queries. These track queries are directly assigned to be a negative prediction and suppressed. Any unassigned ground truth objects are then matched with the proposal queries using a bipartite matching algorithm such as the Hungarian assignment algorithm. These proposal queries take on a specific track ID for future time steps, becoming matched track queries. The key takeaway here is that in standard assignment, only the proposal queries are considered for the unassigned ground truths, while unassigned track queries are automatically suppressed as background predictions. Here we illustrate our modified assignment, where we give the unassigned track queries a second chance to be assigned by also considering them in the matching of the unassigned ground truths. Given the unassigned track queries a second chance to be assigned leverages their inherent confidence to detect these rare newborn track cases. With these two innovations, track query dropout and second chance assignment, we are able to achieve a significant reduction in false negatives, closing the gap between LiDAR TBD and TBA. Here we have the results compared to the previous LiDAR tracking by detection and tracking by attention methods. We see that SCATR outperforms the previous state-of-the-art LiDAR tracking by attention methods, JDT3D, significantly on the A-mode metric and the false negative metric, significantly reducing the number of false negatives from almost 30,000 to about 22,000. This significantly closes the gap between LiDAR TBA and TBD, beating Centerpoint but still doing worse than SimpleTrack. It's interesting to note that while the A-mode is still behind by several percentage points, SCATR achieves similar, if not better, error rates compared to these tracking by detection approaches. This is mainly due to how the A-mode metric is computed, since it equally weighs all object categories rather than considering the distribution of the dataset. Thank you for watching. For further details, results, and ablations, please refer to our paper.